Hello friends, welcome to EK lectures. In this lecture we will be discussing about the applications of Gauss law. Consider a point charge Q placed at a distance L from a circular disk of radius capital R. Find the flux through the disk. So to find flux we need to consider a small area here where we consider it as the small area uh, through which the flux comes out. So this is a perpendicular outward, that is the ds. Now yeah now this can be considered that it is at a distance of small r from the center, and this is the point where we have the charge, and the electric field will be moving to this area in this direction. So here we have the electric field which is in the direction of let it be some r cap, okay, and this area element will be in the n cap direction. Now the angle between them, let's call it as theta, that is the r vector and n. And for simplicity, let us consider only the upper half of this circular disk. That means we are going to find out the flux in the upper half of the disk, and then we are going to multiply it by 2 so that we can get the flux through the total circular disk. Now so electric field at this point will be, so this is L, this is small letter r, so this will be equal to root of L square plus r square. So electric field is kq divided by L square plus r square in the direction of r cap, and ds will be equal to ds n cap. Now the ds for a disk in polar coordinates, let's say it is a function of r and let's say phi, r phi. So ds will be equal to r dr d phi, and the flux, the total flux is flux means the total flux in the upper half, so that will be E bar dot ds bar. So that's equal to integral kq divided by r square plus L square into r dr and d phi into r cap dot n cap. So r dot n cap. So r dot n cap is nothing but cos of the angle between r and n. So that's equal to kq divided by r square plus L square r dr into cos theta into d phi. Now let's take the common things out. So kq integral, and let's write what is cos theta here. From this, cos theta equal to adjacent side, this is the angle theta, same as this one. So adjacent side is L and hypotenuse is root of, so cos theta equal to L divided by root of L square plus r square. So that's r dr into L divided by this. Here we have r square plus L square, so r square plus L square whole to the power 3 by 2, because here we have r square plus L square to the power 1. This is r square plus L square to the power 1 by 2. So into again d phi. So that's equal to kql into integral d phi is so since we are dealing with only the upper half, it is 0 to pi, and the dr r value is ranging from 0 to capital R. So this is 0, r is 0 here, and r is equal to capital R at this point. So 0 to r and 0. So kql into 2 pi, phi is 2 pi, so that is pi integral r dr divided by r square plus L square whole to the power 3 by 2. So flex can be written as kql into pi integral r dr divided by r square plus L square whole to the power 3 by 2. Now integral x dx divided by x square plus a square whole to the power 3 by 2 equal to minus 1 divided by x square plus a square whole to the power 1 by 2. So here again we have this from 0 to capital R, so that's equal to kql times pi minus 1 divided by r square plus L square whole to the power 1 by 2, and this is from 0 to capital R. Since it is minus sign, we can go with the 0 limit first. So kql pi, so going with the lower limit, r equal to 0 means 1 by L minus here we have 1 divided by capital R square plus L square whole to the power 1 by 2, and this is flex through the upper half. So flex through the upper half, and now to the lower half, the total flex will be equal to 2 times that, so 2 kql pi into 1 by L minus 1 divided by r square plus L square whole to the power 1 by 2. Now this k is equal to 1 by 4 pi epsilon naught. So 2 if we multiply by 2 pi, it becomes 1 by 2 epsilon naught. So here if you bring this L inside this bracket, so this becomes q divided by 2 epsilon naught q divided by 2 epsilon naught into 1 minus L divided by root of R square plus L square. Gauss law application. We are going to see uniform charge distribution problem. Problems are based on uniform charge distribution. Now here we have a hollow sphere, and the question is to find the electric field inside the hollow sphere, outside the hollow sphere, and on the sphere. Okay. Now the first case is inside the hollow sphere. Now inside means we can consider any point here where it's P, and this is the center of the sphere, and this is the point where we want to find out the electric field. The radius of the sphere or the hollow sphere can be considered as capital R, and the distance that P from the center is smaller. Now from this you can write that R is less than the capital R. Now according to the Gauss law, we can write closed integral E bar dot ds bar equal to q by epsilon naught. Now the electric field on, if you draw one circle or a sphere, everywhere the electric field will be same on this line, on this at a distance r from the center. Everywhere the electric field will be same because electric field depends on r. So since electric field is same, E into integral ds equal to q by epsilon naught. So integral ds is nothing but the surface area of the sphere into not the surface area of the sphere, surface area of the sphere formed by the radius small r. So that's E into 4 pi r square. So that's equal to q by epsilon naught. And since q is a 0, because there is no charge enclosing this sphere. Now this is the sphere that we need to consider. Inside this sphere there is no charge, that is 0. So E equal to 0. That means the electric field is 0. Now this surface that we have considered is called Gaussian surface. So if you are going to find the electric field inside, we need to consider a Gaussian surface inside, such that within that radius there is a symmetrical surface with the radius r. So that is the Gaussian surface. So electric field inside is 0, so we can write E inside equal to 0. Now for r greater than capital R, now we are going to find the electric field outside the sphere. Outside the sphere. So the Gauss law says integral E bar dot ds bar equal to q by epsilon naught. Now um, here is the center of the sphere, and this is the point P where we are going to calculate the electric field. So calculate the distance r from that and draw a sphere enclosing this original sphere. So now E electric field at all these points, dotted line will be equal to same. So E into 4 pi r square equal to q by epsilon naught. Now let's say that the total charge q is equal to capital Q by epsilon naught, because uh, let the total charge carried by the uh, sphere be q. So E is equal to capital Q divided by 4 pi epsilon naught r square. Now when on the sphere means when r equal to capital R. Now this is to be applied only for r equal to capital R, only for electric field outside. We cannot apply this when electric field is inside to the formula. So here we can apply, but not we cannot apply it to the previous formula. So on the sphere means r equal to capital R. So electric field will be equal to capital Q divided by 4 pi epsilon naught capital R squared. In conclusion, what we can find is, for hollow sphere we have the electric field as follows. For r less than capital R, electric field is 0, and for r equal to capital R, electric field is given by kq by r squared, and for r greater than capital R, electric field is equal to kq by r square. Now when you in the graph, if you can plot the radius along the x-axis and the electric field along the y-axis, we can know that this is the r, and here we can write capital R, and from 0 to capital R the electric field is 0. That means inside. So if you consider this as the sphere, so this is the sphere, and at the boundary or at the surface or on the hollow sphere, you have the electric field given like this. So electric field is this, and as you move away from the surface, the electric field decreases, because as r increases the electric field decreases. So it will be like this. Here it is proportional to 1 by r square, and this is the maximum value of the electric field, and that maximum value is found at the surface of the hollow sphere. Here we have a solid sphere of radius capital R, and here we have to find out the electric field inside, outside, and also on the sphere. Now here we have to define a quantity called volume charge density. Since we are dealing with the uniform distribution, so this is uniform distribution. So volume charge density, it's usually given by rho, and that's equal to total charge on the sphere divided by the volume. So total charge is equal to capital Q, and volume is 4 by 3 pi capital R cube. So this is the volume charge density rho. Now first point is we are going to find the electric field inside the sphere. Electric field inside the sphere. So to find out the electric field inside, for example, we are going to find the electric field at this point, which is at a distance, let's draw from this. So this is the point where we are going to find the electric field, which is at a distance r. So we have to consider a small sphere or Gaussian surface similar to the sphere with the radius smaller, and this is where the point P is, where we are going to find the electric field. Now according to the Gauss law, we have closed integral E dot ds equal to Q by epsilon naught. And what is this Q equal to? This is Q enclosed by Gaussian surface. Now what is the Gaussian surface here? What is given in this yellow color is the Gaussian surface, and whatever is inside this Gaussian surface, or the amount of charge inside this Gaussian surface, is what is given by Q. Now since we are dealing with the electric field inside, you can write small letter r is less than the capital R. So how to calculate the Q enclosed? Q enclosed will be equal to the volume enclosed into the densities. That is, density means this is volume charge density. Volume charge density, then write rho. So V enclosed into rho gives you Q enclosed, or I can write Q enclosed. So to get that integral, so since E is common or E is constant, you can take E outside. So E into 4 pi r square equal to 1 by epsilon times V enclosed. V enclosed is equal to 4 by 3 pi small r cube. So this is this volume of this sphere. that is given in the yellow color. So volume enclosed into rho, that's uh, rho here. So now we can write E is equal to whatever we have common, we can cancel it out. 4 is there, 4 pi, and here pi, and r square we can bring it there. So what is it is 1 by epsilon times rho by 3r, so that you can write it as rho r into 3, so that's equal to rho r by 3 epsilon naught, so that's equal to the electric field inside. So this is electric field inside. Now we can write this electric field inside in terms of the total charge also. So uh, electric field is equal to, from this equation, uh, or you can use this equation as well. So electric field is equal to uh, 1 by epsilon times 4 by 3 pi r cube into rho. Rho is nothing but capital Q divided by 4 by 3 pi capital R cube. So capital Q divided by 4 by 3 pi capital R cube. So here as well we can cancel out the quantities. Here we have E into 4 pi R square. So E 4 pi R square. So here 4 by 3 you can cancel, pi can be cancelled, so this can be written as electric field equal to 1 by 4 pi epsilon naught r square, and r that gets there, so capital Q r by capital R cube. So that's what remains. So 1 by 4 pi epsilon you can write it as k, so k q r by r cube. So electric field, another formula for electric field inside is equal to k q r by r capital R cube. So what we can understand from here is electric field inside is proportional to R, or directly proportional to R. As R increases, the electric field inside the solid sphere increases. For the R greater than the capital R, which means outside the solid sphere, outside the solid sphere, we have to consider a Gaussian surface somewhere outside the so this is with radius capital R, so we have to consider a Gaussian surface here. So that's the Gaussian surface, and this is small r. So E times 4 pi r squared equal to oh, q enclosed by epsilon naught. So what is the q enclosed? Q enclosed will be the total charge q by epsilon naught. So E will be equal to um, capital Q by epsilon naught into 1 by r square. Here you can write 1 by 4 pi. So that's equal to 1 by 4 pi epsilon naught capital Q by r square. Now for r equal to capital R, now for r equal to capital R we can write this is outside, the electric field outside, which is equal to k q by r square, that's E out. So that's now when r equal to capital R, what we can do is put small letter r equal to capital R from this equation. So E out on, not out, it is E on the surface, that's equal to k capital Q by capital R square. Now let's draw the figure. So I mean the graph. The distance versus the electric field. At 0 there is no charge enclosed, so electric field is 0, and we know that from this is up to the radius r, and after that it is increases. And now the electric field inside is kqr by r capital R cube. So capital R is constant, but here small letter r is the variable, so it is directly proportional to r, and this is the point. So up to capital R it is directly proportional, and from that point downwards it is inversely proportional. So here it is directly proportional to R electric field. Here we have electric field proportional to 1 by r square. At what distance outside the solid cylinder, electric field becomes half that on the surface. Here this is the blue color, that is the cylinder with carrying some charge Q with rho as the volume charge density. Now this is the axis, and this is the radius of the cylinder, and at this point if you assume that the electric field is E, and at a distance small r from the center there is a point P where the electric field is E by 2. Now the question is to find what is this distance. That is what we need to calculate. So according to Gauss theorem, we have closed integral E dot ds equal to q enclosed by epsilon naught. So let us write down what is the left hand side now. So E is constant, so E into integral ds equal to q enclosed. Q enclosed is rho into volume enclosed divided by epsilon naught. So this is equal to E into this Gaussian surface is the white colored cylinder, and that is 2 pi r into L, where L is the length of this solid cylinder. So equal to um, rho times volume enclosed. Volume will be equal to uh, pi r square L. So pi r square L into the, also that's a volume, divided by epsilon naught. Now we can cancel out the common terms. So pi is here, r and r, L and L gets cancelled. So electric field E is equal to rho r divided by 2 epsilon naught. Okay, here we have made a mistake here. That's this is capital R, because this is the radius of the cylinder. Volume enclosed, so here this we need to write volume of the cylinder. So that's pi r square, that cannot be cancelled, so r doesn't cancel, so we will rewrite this E into 2 pi small r L equal to rho pi r square L. L is what is that? Yeah, L divided by epsilon naught. That's E equal to, so pi and pi gets cancelled, L and L gets cancelled, so rho r square divided by 2 epsilon naught r, so 2 epsilon naught r. So this is the formula for electric field outside. So electric field on the surface, this is what we need, that is our electric field. So on the surface will be where small letter r equal to capital R, so we get rho r divided by 2 epsilon naught. Now somewhere E dash is equal to E by 2, that's equal to this rho r divided by 2 epsilon naught r into 2, so rho r divided by 4 epsilon naught. So half that on the surface. So if these two are equal, which means you can write it as this formula, that is rho r square divided by 2 epsilon naught into r equal to half rho capital R square, sorry, rho r divided by 2 epsilon naught. So in this rho and rho gets cancelled, r and r can be cancelled, so from this you get r is equal to 2 times r. So when small letter r equal to 2 times r, the radius the electric field becomes half. So if this is this distance is capital R, so what about this distance? That will be equal to R, because this entire distance is 2 times R. Now so far we have been dealing with the finding the electric field using Gauss law. Using Gauss law, and we were dealing with uniform charge distribution. Uniform charge distribution, which means that the charge is distributed in a certain uh, object uniformly, whether you take a sphere or a cylinder, or you have a cube or any plane surface. In all these cases we had uniform charge distribution and charge density. Uniform charge distribution means charge density is constant. It does not vary with respect to the space. uh, each point on the body or the object will have the same charge density. So that's what is meant by uniform charge distribution. Okay, now we also have seen how to go forward with the Gauss law, that is closed integral E bar dot ds bar E dot ds equal to q encircled by epsilon naught. Q encircled is a charge enclosed by Gaussian surface. Enclosed by Gaussian surface. That means whatever charge is inside the Gaussian surface, we used to find in this way. That much charge will be contributing to the uh, electric field or the flux. All right, now taking the first part, that means if you are finding the electric field inside the body, if you are finding the uh, electric field inside, then you have to take Gaussian limits, or Gaussian limits. That means the integration is from 0 to small r. This EDS, the integral will be from 0 to r. Wait a minute, that is for q encircled. Q encircled, the Gaussian limits. For example, if this is the sphere and we are finding the electric field inside, somewhere here we have to find out the electric field, then from the center we have to draw a smaller circle, smaller sphere. This is a solid sphere, and here inside that we have to draw another sphere of radius r. So inside means we have to take the Gaussian limit 0 to r to find out the total charge. So total charge q will be equal to integral rho dv. Now this dv integration is from 0 to small r. Now if we are finding the electric field outside, then we have to take the body limits. That means we have so we are finding the electric field here, then 0 to r, this is r, then the total charge q will be equal to integral rho dv. So you have to integrate from 0 to capital R, not the small letter r, because there is charge present only up to this point. After that there is no charge. Charge will be present only in the sphere, which is given in the red color. After the red color, that means the sphere, there is no charge, so there is no need to integrate from r to small r, because here there is no charge density. Charge density is available only in this region. So this is 0 to capital R. So body limits 0 to capital R. Now Gauss law for non-uniform charge distribution. Gauss law application for non-uniform charge distribution. Now Gauss law says that closed integral E dot ds equal to q encircled by epsilon naught. Now let's take the first thing, that is q encircled. How to find the q encircled? Q encircled means it's nothing but rho dv. Rho the charge density and dv the small change in volume. And there will be usually two cases. One is a sphere, and for sphere dv is equal to r square dr sine theta d theta d phi. And for cylinder, another case is we get a cylinder, and there we will be using cylindrical coordinate system. And for cylindrical coordinate system, dv equal to r dr d phi dz. We have been using rho d phi dz, but in the case of charge density we might use rho, so that's the reason why we are using r dr d phi dz. Now similarly, as we have proceeded with uniform charge distribution, if we are finding the electric field outside, then finding q encircled, for finding q encircled, your integral limits are from 0 to capital R, or you need to write body limits. And if you are finding the electric field inside, then q encircled, the integral is the Gaussian limits, Gaussian surface limits, that is 0 to small r. Spherical charge distribution. So here we have given the rho of r. Rho of r means the spherical charge distribution density, that is volume charge density is given. Density rho of r. Unlike the uniform charge distribution, here the rho of r is equal to cr. That means rho is proportional to c times r, because as it is a non-uniform charge distribution, this indicates it is a non-uniform charge distribution. and this charge density is only up to the radius. That means from here to here, as you go from 0 to the capital R, the charge density increases. Here it is low. As you go away from the center and reaches the surface, the charge density is keep increasing as a function of R. So if you could draw the charge density as a function of the distance rho of R, this is distance R, then C of R, it increases like this. So it's a linear curve, that is rho, as rho depends on the distance R. Now, which indicates that this is a uh, non-uniform charge distribution. Now, as the we have to find the electric field inside. So electric field inside. So if we want to find out the electric field inside, that means let's take a point inside here, somewhere over here, which where we have to draw the Gaussian surface. So this is Gaussian surface with radius R. So the value of R is less than the capital R, because this is small r that is inside. So since it is inside the sphere, the radius of the Gaussian surface R will be less than the radius of the sphere. So R is, a small letter r is less than the capital R. So applying the Gauss law, that is E dot ds equal to q by epsilon naught, or q encircled by epsilon naught. So the electric field is being constant at distance r, so E into ds, that is 4 pi r square. So E into 4 pi r square is q enclosed. Charge enclosed can be written as integral rho dv, charge density into dv, then divided by epsilon naught. So now we need to find out the integral rho dv. Now that integral is from 0 to small r, because we are finding it inside. So what is rho inside? Rho inside r less than or equal to capital R. Up to r less than or equal to capital R, the rho is equal to CR. So integral 0 to r CR and dv. Now for spherical polar coordinates, dv equal to r square dr sine theta d theta d phi. So substituting the dv value, r square dr sine theta d theta d phi. Now we have triple integral, and solving this we get integral c r into r square is r to the power 3 r cube dr, then integral sine theta d theta. This theta value is from 0 to pi, this is from 0 to small r, and d phi integral, phi value is from 0 to 2 pi. Now this is c r cube. R cube integral is r to the power 4 by 4. So c r to the power 4 by 4 with the limits 0 to small r. Then sine theta is integral is minus cos theta. Again integral is from 0 to pi. Then integral d phi is phi, and its limits is from 0 to 2 pi. This becomes CR to the power 4 by 4 because the limits are from 0 to R, minus cos theta, lower limit first, that is cos 0 is 1, cos pi is minus 1, so 1 minus minus 1 into 2 pi minus 0, 2 pi minus 0. So you get the Q total charge enclosed equal to C R power 4 by 4 into 1 minus minus 1 is 2, 2 into 2 pi is 4 pi, so it's C pi R to the power 4 or pi C R to the power 4. This is equal to Q enclosed. So now we have the Q enclosed equal to pi C R power 4. So applying the Gauss law, we have E times 4 pi R squared equal to Q enclosed by epsilon naught, that is pi C R to the power 4 by epsilon naught. Now from here we can cancel out the common terms on the right, both sides, pi and pi, r square, and here r power 4, it becomes r squared. So the electric field will be equal to pi c r squared by this 4 will come here, so 4 times epsilon naught. So this is electric field inside. Now similarly we will proceed for the electric field outside. So electric field outside, here we have to consider the small r is greater than the capital R. So somewhere outside we have the point P where we have to find out the electric field. Similar to with the R as the radius, we have to construct a Gaussian surface which will be of this form. Yes. So we have constructed the Gaussian surface and now we need Q enclosed. So the left hand side will be equal to E into 4 pi r squared. Similarly here Q enclosed by epsilon naught. Now what is Q enclosed? That's equal to integral rho dv. Since we are finding outside the electric field outside, we have to consider the uh, body limits 0 to capital R or whatever body limits we have. So that's equal to integral rho is C R r square dr sine theta d theta d phi. All are the limits. Now here also we have the integral. This also this is 0 to capital R, this is 0 to pi, and this is 0 to 2 pi. So when you integrate you get C r cube integral is r to the power 4 by 4. This is from 0 to capital R, and this we already have seen, this integral is equal to 4 pi. So that's equal to pi, this is substituting for r equal to capital R, so pi c capital R to the power 4. So this is Q enclosed. Now applying the Gauss law, that is E into 4 pi r squared equal to Q enclosed is pi c capital R to the power 4 by epsilon naught. Now here we have to cancel out the common terms. Only common term here is pi and pi. So remaining we have to substitute. So electric field is equal to Cr to the power 4 Cr to the power 4 by 4 epsilon naught r square. So 4 epsilon naught r square. This is E out. Now if you want to find out electric field on the surface, we have to substitute r equal to capital R. So then we get Cr to the power 4 by 4 epsilon naught small letter r equal to put capital R square. So that's equal to Cr square by 4 epsilon naught. Here we have made a small mistake. This pi we already have cancelled it, so it says Cr square by 4 epsilon naught. So this is electric field on the surface. This is electric field outside, and this is inside. So when you draw the graph, it will be something similar to this. We'll see that. Now here we are going to draw the graph, the electric field inside. So this is our capital R and capital R here, the radius of the sphere, and along this direction we have R, the radius vector, that is the distance. Okay, now from here is where we write this is our electric field, and this is the R, which depends on or electric field which depends on R. Now in the first case, inside means this is what, from here to here it is inside the sphere. So in the inside it is directly proportional to r squared, so the graph goes like this, and on the surface it is Cr square by 4 epsilon naught, which is constant, and once it is outside, it again decreases in the same pattern as it increased. So here in the first case it is directly proportional to r square, and in the second case it is inversely proportional to r square. Here we have a similar question. In this case, rho of r depends on a by r. So a is some constant. So let's start finding out from E outside. So for E outside, the radius will be, or the point r will be greater than the capital R. So the left hand side, that is E into 4 pi r square, remains constant. Now that's equal to q enclosed by epsilon naught. Now what is q enclosed? That's equal to integral rho dv. Now integrating integral a by r square dr sine theta d theta d phi. Now this sine theta integral is from 0 to pi and integral 0 to 2 pi. Now this integral sine theta d phi, this accounts for 4 pi. Now this is integral a by r, sorry, a into r dr. So this is 0 to, since it is outside, 0 to capital R. So 4 pi will be outside. So 4 pi into AR, A is also constant, R dr is R square by 2, and the limit is from 0 to capital R. So 2 to 4 gets cancelled, so that is 2 pi A capital R square, that is Q encircled. Now electric field E out into 4 pi small r square is equal to Q enclosed is 2 pi A capital R squared divided by epsilon naught. From here we can cancel out whatever is common. Pi and pi gets cancelled. Here we have uh, 2, so 2r square A r square epsilon. So E out is equal to AR square by 2 epsilon naught r square. That's the electric field outside. So electric field on the surface will be equal to where R is equal to capital R, that will be equal to uh, E A by 2 epsilon naught. So that's E on. Now we need to calculate the E inside. E inside, for that we know R should be less than the capital R. So E inside into 4 pi small r square equal to integral rho dv. So integral we have already found out, that is AR AR square by 2. So 4 pi A R square by 2. This is integral was from 0 to small r, and that's the that is equal to 2 pi A r square. So electric field inside into 4 pi small r square equal to 2 pi A r square by epsilon naught. So this implies E inside equal to cancel out the common terms, pi 4, this is 2 times, this gets cancelled, r square and r square gets cancelled, so what's remaining is A by 2 epsilon naught. So A by 2 epsilon naught. So this means that inside the electric field and on the surface it's constant. So if you draw this R and this is electric field, from 0 to capital R, let this be capital R, you have a constant electric field, and from that onwards it is inversely proportional to the R square, so that decreases like this. This point is A by 2 epsilon naught. From that it decreases. Here are some questions for practice for spherical charge distributions. This is rho of r is equal to ar squared for r less than or equal to r, and otherwise it is 0. And we are asked to find out the electric field inside, outside, as well as on the sphere. Now another question is rho of r equal to uh, rho naught r sine theta, rho naught r sine theta for r less than or equal to r. And another question is rho equal to rho naught into 1 minus r square by capital R square. Okay, in all these cases, question number 1, 2 and 3, you have to find out the electric field inside, outside, as well as on the sphere. Here we have a problem based on the solid cylinder where rho of r equal to cr for r less than or equal to capital R, and for outside, that is for small r greater than capital R, the charge density is 0. Now applying the Gauss law, we have closed integral E bar dot ds bar equal to q enclosed by epsilon naught. Now let's see for electric field. Let's start with the outside. E out for r greater than capital R. We have to find some point here outside. Then let's say here, somewhere here. Then we have to consider from the center we have to draw a radius r. Then we have to consider the with the radius as r, we have to draw a cylinder. So this is the cylinder that we have to consider. Since we don't have to deal with the L, why? Because the electric field along this direction uh, both will be equal to 90 degree. So electric field, we have to consider only the uh, electric field in this region. Electric field here and the area vector here and the electric field in this direction makes 90 degree, and it gets cancelled. So now E out equal to E out into now ds, integral ds equal to integral rho dv, that is q enclosed by epsilon naught. From here, integral ds, the area is for the cylinder, integral ds surface area is 2 pi r, that is the circumference, into the length L, which is the length of the cylinder. So total surface area of the cylinder is 2 pi RL. Okay. Now coming to the integral rho dv, that is q enclosed. So q enclosed will be equal to integral rho dv, that's equal to integral rho is cr, so cr dv. Now dv in cylindrical coordinate system is r dr d phi dz. Okay. Now integral rho dv can be written as cr, dv is r dr, d phi dz. Now d phi is integral limit from 0 to 2 pi, and dz is limits from 0 to L, where L is the length of the cylinder, or we'll write small letter L because we have already seen the length of the cylinder as L. Now integrating this, what we get is integral C r square dr. That integral is from 0 to capital R. Then integral d phi is 2 pi, and dz integral L. So this is constant now. So 2 pi LC into integral r square is r cube by 3, and the limits from 0 to r. So the integral yields 2 by 3 pi LC capital R cube. So this is the enclosed charge. Now E into 2 pi RL, so E out into 2 pi RL is equal to Q enclosed is 2 pi LC capital R cube by 3 epsilon naught. Now cancelling out the common terms, so 2 pi L and L. So C capital R cube by 3 epsilon naught R. So that gives C capital R cube divided by 3 epsilon naught R. So this is the electric field outside. Now from here we can find out the electric field inside, equal to where R equal to capital R, put R equal to capital R, then we get C capital R square by 3 epsilon naught, and that's the electric field inside. Sorry, this is on. Now we have to find out the electric field inside. Now we are going to see how electric field inside, somewhere the point you can consider here. So we have to draw a Gaussian surface such that on either side we have equal cylinders. Okay, so something like this. Yeah. On the right side, what you see is the yellow color is the Gaussian surface, and this is the distance or the point at which we have to calculate, or let this be the P, and this is the radius of the Gaussian surface, or the distance at which we had to find out the electric field from the center of the cylinder axis. Now for that we will start with the integral E dot ds equal to Q enclosed by epsilon naught. Now Q enclosed will be equal to integral rho dv, since we are finding out it inside, integral C r dr d phi dz, and the limits are from 0 to small r because we are finding out inside. So that's equal to CR square dr integral, then integral d phi integral dz. So that accounts for CR cube by 3, d phi is 2 pi, dz is L. So that's Q enclosed, and similarly we have E inside into 2 pi r into the length equal to Q enclosed is CR cube 2 pi L by 3 epsilon naught. Here we try cancelling out the terms. 2 pi and 2 pi gets cancelled, L and L, R, and here we have square left. So electric field inside is equal to CR squared by 3 epsilon naught. So as practice work, find the curve for electric field as a function of R. So electric field versus R for cylinder with the given condition on rho. So we know that what is the rho. Rho is CR. So based on the rho, we have to find out the curve. So this let it be your work. Here consider a two solid sphere of charge density rho. So this let it be rho, and here you have minus rho, overlapped with each other, and find the electric field in the overlapped region. So somewhere here we can find one particle and one point P, and this is where we are going to find out the electric field. Okay, so let's find out its origin. These are the two centers, and from this to this you have, let it be R plus, indicating the vector in the positive density region, and here you have R minus, and this is a vector in this direction. Okay, now what is the D, this distance between this separation? Now let this be the D, and this is R plus and R minus. Now the electric field inside, we have seen it is equal to rho R by 3 epsilon naught, and this R is in the direction of R vector. So this is inside for a charge. So this is if I write it for positive charge, and for negative, E inside will be equal to minus rho R cap by 3 epsilon naught. This will be R plus, this will be R minus. So the net electric field will be the sum of the E plus E and minus E. So that's equal to rho R plus, let's write in the form of vector, by 3 epsilon naught minus rho R minus by 3 epsilon naught. So this gives us rho by 3 epsilon naught as constant, R plus vector minus R minus vector, R plus minus R minus. So uh, this vector minus this vector is nothing but the vector d. This is because when you have a triangle, first vector is this vector r1, if this is r2 in this direction, then the third side, that is in the triangle of the third side, then this vector is r1 minus r2. Okay, so that's equal to rho d divided by 3 epsilon naught.